Welcome to this session of Materials Engineering. Myself, Anirban Sarkar, Assistant Professor, Department of Mechanical Engineering of JS College of Engineering, Kollam. Today's session, we will discuss about the plastic deformation of metal. We know that when a metal is stressed below its elastic limit, the resulting deformation or strain produced in the metal is temporary. This strain or deformation vanishes after the removal of stress and metal goes back to the original dimensions. When it is stressed above the elastic limit, plastic or permanent deformation takes place, and the metal does not return to the original shape after the removal of stress. So, the ability of metal to undergo plastic deformation is one of the important properties which is utilized for shaping of metal by various fabrication processes such as rolling, forging, drawing, extrusions, etc. Therefore, it is necessary to study the mechanisms by which plastic deformation occurs so as to assess the behavior of metals under the various fabrication process used in shaping of metal. The plastic deformations may take place by slip or by twinning or simultaneously both slip and twinning. So first of all, we will discuss the mechanisms of plastic deformation by slip. Slip, it represents a permanent displacement of one part of crystal relative to other, shown in this figure. This is due to movement or sliding of atom one over another. The plane on which it occurs, it is called a slip plane. Here you can see a discrete blocks of crystal above and below the slip planes or between the two slip planes remain undistorted as shown in the first figure, that is before slip. So if we apply some load or stress, that further deformation occurs, and it may occur either by movement of blocks on existing slip plane or by the formation of new slip planes. Slip always occurs in certain crystallographic plane and definite directions. The planes on which slip occurs are called slip planes, and the direction in which occurs is called slip directions. In each crystal system, the slip planes and slip directions are mostly well defined, and they may be one or more. Slip planes usually occurs at most closed packed planes, that is planes of maximum atomic density. Such planes obviously will be widely spaced, that is the interplanar distance between such planes is more. The slip direction is the direction in the above slip plane in which the atoms are most close to each other. that is linear atomic density is highest. Thus, in a closed pack hexagonal crystals, slip usually occurs on 0001 basal plane in the direction of type, that is 1120. In FCC structure, slip occurs on the plane of type 111 and in the direction of the type 110. In BCC structure, slip simultaneously occur on many planes of type 110, 211, 321 in the direction of type 111. It does not restrict to any one family of plane. Due to this, slip lines observed in HCP and FCC structure. BCC crystal usually occurs on the planes of 110 at low temperature. A slip plane and slip directions in the plane constitutes a slip system. Now, the probable slip plane and slip directions are given in this direction. Now, slip results from the motion of dislocation from one place to another place. There are two basic type of dislocation movement, such as called as glide and climb. In glide, the dislocation moves in a surface defined by the line and Burgers vectors. That is, glide is a conservative motion of dislocation. In climb, the dislocation moves out of the glide surface and therefore climb becomes an non-conservative motion of dislocation. Slip is the most common manifestation of glide. The energy required to move a dislocation is proportional to is capital GB square, where G is the shear module of the metal or material through which the dislocation moves, and B is the Burgers vector. It indicates that the dislocation had short Burgers vectors require less energy for the motion and hence move most readily. The Burgers vectors is shortest along the closed pack directions and hence the stress required to move a dislocation is least in this direction. Next is mechanisms of twinning. Twinning is a process in which the atoms in a part of crystal subjected to stress rearrange themselves so that the orientation of the part changes in such a way that distorted part became a mirror image to the other part. So as shown in this figure, that a part of crystal is just a mirror image of the another part. The plane across which two parts are mirror image is called twinning plane or compression plane. Every plane of atoms shift in the same direction by an amount proportional to the distance from twinning plane. Therefore, twinning can be defined as an homogeneous shear of the lattice parallel to the composite plane. The direct contribution to the plastic deformation by twinning is negligible. However, twinning creates favorable condition for slip and total deformation increases due to indirect contribution by twinning. Twinning occurs by plastic deformation or by thermal treatment. Twinning, which occurs by plastic deformation, is called deformation twinning and is most common in HCP crystals. This also occurs BCC structure at low temperature. The type of twinning particularly occurs under the fast or soft loading condition. The twinning which occurs by thermal treatment is called annealed twinning and occurs in some metals and alloy which FCC structure such as copper, silver, and austenite stainless steel. Like slip, twinning occur along certain crystallographic plane and direction as given in this table. The plane and directions are called twin plane and twin direction. And the twin plane and twin direction of these HCP, FCC, and BCC structures are given. For HCP structure, the twin plane is 1 0 1 bar 2 and direction is 1 0 1 bar 1 bar. FCC twinning plane is 1 1 1 and twin direction is 1 1 1 1 2. BCC structure twin plane is 1 1 2 and twin direction is 1 1 1. The difference between twinning and slip. Deformation twinning, also known as mechanical twinning, differs from slip in the following way. The twinned portion of a grain is the mirror image of the original lattice, whereas the slipped portion of a grain has a same orientation as an original grain. Slip consists of a shear displacement of an entire block of the crystal, whereas twinning is an uniform shear strain. The direction of slip may be positive or negative, while the direction of shear in twinning is limited to that which produce the twin images. The stress required to produce twinning is higher than the stress required to start the slip. And the last of all, the stress required to propagate twinning appreciably less than required to initiate, whereas the stress required to propagate slip is usually higher than the stress necessary to start the slip. Now next is work hardening or strain hardening. Work hardening means hardening or work hardening, also known as strain hardening, means that the metals became hard and strong during working or straining, and more stress is necessary for further deformation. The stress necessary to cause sleep is always increased after earlier cold water. This is due to the rotation of plane during working. If the critical shear stress for a given crystal is high, that is, if crystal have elastic stress or elastic limit is high, before any sleep, plastic deformation occurs. The crystal fails as soon as the applied stress exceeds the bond strength. And if the critical shear stress is less, plastic deformation starts as soon as the cohesive strength of the material, and failure occurs as soon as the stress exceeds the cohesive strength of the material. From this, it is clear that material having low value of critical shear stress and high value of cohesive strength show more plastic deformation prior to the fracture. Next is cold working and annealing. Cold working is a deformation process carried out under conditions, that is, where recovery process are not effective. So generally, the cold working is done below recrystallization temperature, and hot working is deformation under condition of temperature and strain rate such that recovery process takes place simultaneously with the deformation, and it is done generally above the recrystallization temperature. Structural changes during the cold working of polycrystalline materials and alloy, that is, first of all, changes in shape and grain size of the grain. The aqueous grain on deformed are elongated in the direction of acting force, that is, stretched in the direction of main tensile deformation stress. Changes in orientation of grain, preferred orientation or texture of the state of several cold worked metal in which certain crystallographic plane of the grain oriented themselves in a preferred manner with respect to the direction of stress. Changes in internal structure of grain during cold working, around 15% of the work of the deformation get aborted in the metal. The stored energy is the form of energy of the crystal defects. Plastic deformation increases the concentration of point defects. With increases of cold working, number of stacking failure increases. Thus, density of extended dislocation increases. The number of dipoles, jogs, prismatic loop plinths also increases. The most important internal changes of structure increase in density of dislocation from 10 to the power 10 to 10 to the power 10 to the power 5 to 10 to the power 8 per centimeter square in annealed state to 10 to the power 10 to 10 to the power 12 by moderate cold water. Now, this is the comparison of mechanical properties during recovery, recrystallization, grain growth during cold working and annealing of metal. So, as we will see, that is the strength, the ductility, and hardness and residual stresses, these are the given. The ductility increases with the recrystallization and grain growth. The strength hardness is decreases over the recrystallization and grain growth. Now, effect of cold working on properties. Cold working or strain hardening is the increases in the stress required to cause further slip because of previous plastic deformation. It is an important industrial process that is used to harden metal or alloy that do not respond to the heat treatment. It changes various mechanical, physical, and chemical properties of metal and alloy. With increasing amount of cold work, ultimate tensile strength, yield strength, hardness increases, but ductility decreases. Cold work texture and mechanical fibering leads to anisotropy in properties of material. The ductility and impact toughness is much lower in transverse section rather than the original section. As the internal energy of cold work state is high, the chemical reactivity of the material increases. That is, corrosion resistance decreases and may cause stress corrosion cracking in certain alloys. The rate of strain hardening is generally lower in HCP metals than cubic metal. High temperature of deformation also lowers the rate of strain hardening. Annealing of cold work material. In certain application, material are used in cold work state to derive benefits of increased hardness and strength. The cold work dislocation cell structure is mechanically stable but not thermodynamically stable. So, it is necessary to restore the ductility to allow the further cold deformation or to restore the optimum physical properties such as electrical conductivity essential for application. The treatment to restore the ductility or electrical conductivity with a simultaneous decrease in hardness and strength is annealing. It is heated cold work material to a temperature above recrystallization temperature, holding there for some time and then slow cooling. It is divided into the three distinct stages, that is recovery, recrystallization and grain growth. There is no change in composition or crystal structure during annealing. The driving force for recovery and recrystallization is the stored cold work energy, whereas for grain growth is the energy stored in grain boundaries. Recovery, it is the restoration of physical property of the cold work metal without of any observable changes in the microstructure. It is the annihilation and rearrangement of point imperfection and dislocation without the migration of high angle grain boundary. Recovery is initially very rapid and more when the anneal temperature is high. Electrical conductivity increases rapidly towards the anneal value, and lattice strain measured using XRD is appreciably reduced. With increased time at constant temperature, the recovery becomes slower. The greater the initial cold work, the more rapid is the initial rate of polygonization. Is one of the recovery process which leads to rearrange of dislocation with a result lowering of lattice strain energy. It is a process of arranging excess edge dislocation in the form of tilt boundary and the excess screw dislocation in the form of twist boundary, with the result lowering the elastic strain. Climb and slip of dislocations are essential for polygonization. Recrystallization, it is the nucleation and growth of new strain-free crystal from the cold work metal. Kinetics of recrystallization resembles a phase transformation. Two distinct nucleation mechanisms have been identified. That is strain-induced boundary migration, where a strain-free nucleus is formed when one of the existing grain boundaries into its night, leaving a strain-free recrystallized region. New grains are formed in the region of sharp lattice curvature through subgrain growth. This seems to inclusion or second phase particles. Mechanical properties changes drastically over a very small temperature range to become typical of the annealed material. And electrical resistivity decreases. Factors influencing recrystallization, that is amount of deformation, temperature, time, initial grain size, composition, amount of recovery, method of deformation. Hence, recrystallization temperature is not a fixed temperature at the sense of a melting temperature. It is defined as the temperature at which the given alloy in a highly cold work state completely recrystallized in 1 hour. The law of recrystallization are a minimum amount of deformation is needed to cause recrystallization. Smaller in degree of deformation, higher the temperature required to cause recrystallization. Recrystallization rate increases exponentially with temperature. Doubling the annealing time is approximately equivalent to increase the annealing temperature. Greater degree of deformation and lower annealing temperature, the smaller recrystallization. Larger the original grain size, the greater the amount of cold work required to produce equivalent recrystallization temperature. The recrystallization temperature decreases with increasing impurity of metal. Alloying always raises recrystallization temperature. And the amount of deformation required to produce equivalent recrystallization behavior increases with increased temperature of water. Solute and pinning effect. The impurity in metal segregate at grain boundary and retardate the migration boundary during recrystallization. This is known as solute drag. When the fine second phase particle lies on the migrated boundary, the grain boundaries is reduced. The grain boundary area is reduced by an amount equal to cross-sectional area of the particle. When the boundary moves further, it has to pull away from the particles and thereby create a new boundary. This increased energy and manifests itself as an pinning acting on the boundary. Consequently, the rate of recrystallization is decreased. Grain growth, it is the uniform increase in the average grain size. Following recrystallization, the grain size distribution does not changes during normal grain. Now, this is the figure that we have discussed earlier, that residual stresses, hardness and strength decreases with the recrystallization and grain growth, that during recovery, grain recovers slightly from the cold working. The residual stresses decreases sharply. The hardness and strength remain unaffected, and ductility slightly increases during recovery. In recrystallization, when the new grain forms, residual stresses also decreases and become stagnant. The ductility increases further, and hardness and strength decreases rapidly. During the grain growth, where larger grains grow at the expenses of the smaller grain, the ductility increases first of all and became stagnant. The hardness and strength lower, and after that it is also became stagnant. So this is the effect of recovery, crystallization, and grain. Thank you for joining this session.